Hi folks, Praveen here. I welcome you to another session on OpenCV. We will be doing OpenCV. I will be studying blurring and smoothing using notebooks on CloudX Lab. So let's first talk about what's blurring and smoothing. So blurring and smoothing are essential tools for any computer vision engineer. It's usually the precursor of the previous step before doing more advanced techniques like edge detection. Now, why do we blur or smooth? Which at first sound, blurring or smoothing sounds like a step in which we would be losing detail. Why do we do that? So, what we want to do with what we often want to OpenCV is we want to identify edges. Now, typically in any real picture, we don't have smooth edges. We don't even have sudden edges. So an edge is essentially in the region when you have a certain value, a certain change in pixel values. Like over here, if I have say pixel values across a particular row, and I have a low pixel values, and it's eventually goes to a higher pixel value. So this is kind of an edge. So in a real image, what I have is I have graininess. I don't have a smooth point in which this jump happened very suddenly, nor is it smoothened out. What I have is some sort of graininess in the middle, and it's very difficult for algorithms to decide if you're given such sort of data of what is the exact point at which an edge should be declared. So what we do is we want to remove this graininess, and to remove the graininess, we apply some sort of averagings, some sort of weighted means in this region to eventually make the pixel values look like this. So once you have pixel values that look like this, you can easily decide what a edge is. So an edge we could choose to have an edge as a midpoint over here because it's nicely smooth, or you could run some functions based on derivative values of the slope, etc. We will look at that more in detail in the future chapters. So, okay, so blurring and smoothing basically involves running a convolution of small kernel. What that means is that you take a small set of pixels at a few at a time, and you do some sort of averaging or a weighted mean around it. Okay, now let's get started. First, we will do the first part where we just set the pictures up. The pictures we'll be working is the giraffe picture, which you've seen before. As you see, it kind of works nicely. The first kind of blurring we will look at is blurring by average, which is exactly what it means. It's going to say that take a small kernel. So we'll take three types of kernels here. So what we've done here is we've created a stack of outputs based on different types of kernels. So we've done a 3 by 3 kernel, a 5 by 5 kernel, and I've taken a 70 by 70 kernel. That's a very large one. This is just to show you how averaging looks like and what it means. Okay, that's all it is. And we're going to show how it looks. So what is happening right now is we're running blurring in three different methods. So you can see how a 3 by 3 kernel looks, how a 5 by 5 kernel looks, and how a 70 by 70 kernel looks. So you can see when you run a 70 by 70 kernel, the image is a lot more blurred than it was before. Now, the next type of blurring we will talk about is Gaussian blurring. In Gaussian blurring, the output is a weighted mean of the surrounding pixels. So before, what we did, we just took the surrounding of the kernel and we just gave in mean. Here, what we'll do is a weighted mean where the pixels that's closer will have a higher weightage. So the closer the picture, the higher the weightage. Again, we create a new type of blurred stack where we do blurring on multiple sizes. And so we have a different kind of blurring effect. The difference is much more starker when we look at 70 by 70. So when we took a very large area, when we're taking the average over here, we took the average. We just take the average value across that kernel of 70 by 70. But here, what we're doing is, since we're giving a weighted mean, only the pixels that are closer to each other have a higher weightage. So we don't see that much. The blurring isn't that strong, but it's often sufficient enough to take out all the graininess of the edges. It's a very recommended. So Gaussian blurring is a recommended form of it, which does blurring without losing too many features. The other blurring that's used is median blurring. So if you got small noise like salt and pepper noise, like small black spots here, it can take it out. What it does, it takes a median of all the pixels in the kernel. Now, what is very important over here is that you have to note that if you're using median blurring, you have to use odd numbers, because a median number, we need a very clear midpoint. Okay, we need a very clear midpoint. That's the reason why I have median blurring. So here what we do, so median blurring, basically you don't you specify the kernel by just one number. It's always a square. It's not a, it's never rectangle. It's always a same sided, same number. So here I use 3, 5 and a 71 by 71, and I can see how it looks like again the same picture. Wait for it, and yeah, you have a picture over here. So this kind of, it looks a little more like the average than the Gaussian, because I'm just going to, we take the we take, there is no weighted, we are not weighing the, there is no weightage for the location, or so we're not giving more weightage to pixels if they're closer to the center. We're not doing that. The last blurring we look at is called bilateral blurring. In bilateral blurring, we use two Gaussian distributions. The first Gaussian distribution does the usual, because considers only the spatial neighbors. That's pixels that's close to each other in that same coordinate space. The second Gaussian basically then also takes a look at gives a weightage for the pixel intensity. So the pixels that have similar intensity are have a higher weightage while computation of the blur. Okay, so it turns out that it does a very good job of reducing noise and keeping edges. It just is a little slower, obviously, because we take we have to take we have to do this. The process is almost twice. We're running two version filters. That's the reason. Okay, okay, folks. Thanks for your time. That's it.